The thing about synthesis, what makes it so difficult compared to any other chapter in organic chemistry, is that up to this point it was very straightforward. You had a reaction topic, you had molecule A, and you were told, react molecule A with something to come up with B, or somehow go from A to B, give me the reagent. But it was very simple and very straightforward. Now that you're dealing with synthesis and multi-step reactions, in class you probably learned A goes to B, goes to C, and it kind of stops there. But on the exam, you're going to be given molecule A. You will be asked to come up with a synthesis pathway or show all the intermediates to come up with Z. That's about as intense as the difference will be between what you had in lecture, what you had on your quizzes and homework, and what you get on your exam. And this is where a lot of students freeze, because not only is it longer and harder, but you're no longer limited to the alkene chapter or the alkyne chapter. Now you have to pull reactions from everywhere, and the question is, how do you do that? The way I like to approach this is not to do a reaction, and kind of find my way from A to Z, because it's very easy to go down the wrong path and get stuck. Instead, I'm going to challenge you to break it down and say, if I don't know how to get to Z, what if I ignore A for a moment and just ask myself what reaction I know that can get me to Z? Maybe I can come up with Y. And I know the general direction that I need to take A to go towards where I need, so let me come up with B. And now I have a much smaller, much simpler reaction to figure out. And I'll show this to you in real life examples. I'll demonstrate it with quite a few problems. But we can do the same thing again. I don't know how to go from B to Y, but I do know that X is going to give me Y. And I can get the general direction from B to C. And look at that. It becomes a much smaller problem. This is what we want to focus on. Now, even with this, a lot of times you look at your question, you start thinking about everything you know, and you get so overwhelmed that your mind goes blank. And so instead of starting with the forward direction or the reverse direction, I actually want you to take a step back and do some busy work just to get the wheels turning, just to get your mind processing. I want you to jumpstart your brain. And specifically, I want you to ask two very, very simple questions. These questions are going to save you so many points because they will help you get in the right direction. Question number one, what's the same? So many students will lose points. I'll look at their problems that they'll show me either from a quiz or an exam. They didn't count the carbons. They didn't recognize what they had to keep. They didn't see what was the same. And question number two is, what's the difference? Before you start reactions, I want you to ask yourself, what's the same? What's the difference, or what is different? And you want to look at a couple of different things. The number of carbons in your chain. Don't be adding carbons if you don't have to. Don't do oxidative cleavage if the number doesn't change. You want to look at the functional group. What is on the molecule? What is reacting? And you want to look at the position of reactivity. Where on the molecule is this happening? Oh, sorry, I thought I muted myself there. Oh, it doesn't actually work. Okay, I apologize. I'm going to be coughing throughout this session because my throat is unhappy and I don't know how to work the mute button on this thing. I apologize up front and I will try to keep it quieter. If you have been busy writing all of this down because you're trying to take good notes and catch everything, I have you covered. If you look at the pinned comment, go to layforSci.com/orgolive. And if you sign up on that page, I will send you a copy of the workshop notes when I'm done, a link to the recording, as well as a worksheet of all the problems that I'm going to go through today. So again, go to layforSci.com/orgolive and you'll get a copy of the recording link, workshop notes, and worksheet for the problems that we're going through today. So with that, are you ready to echoing a bit. Let me see if it'll let me change the audio settings while I'm streaming. Was the echoing fixed? Can you still hear me echoing? Let me know in the comments if A, you can hear me echoing, and B, I want to try something on my mic. So I'm going to say a number. Let me know if you hear the number. If you didn't hear the number, tell me that you didn't hear the number, because I think I figured out how to mute myself and get rid of the echo. All right, it looks like problem solved. It was picking up two audios, one of which I was muting, one of which I wasn't. That means I can cough all I need to today. Excellent. So now that the echo is gone, are you ready to put this into practice and to see how simple we can make synthesis by using this approach? If yes, go ahead and give me a heart. Click on the heart by the comment section. And let's start with a simple practice problem. This is less about giving you a difficult problem and more about trying out the system. Say you see this on your exam, you have to convert this molecule into something that looks like this. The first thing that most students try to do is turn the bromine into an aldehyde, which it's kind of where you want to go, but remember, I am challenging you to take a step back and to ask the two questions. Question number one, what is the same? We're looking at the number of carbons, the functional group, and the position of reactivity. The number of carbons, I have 1, 2, 3. In the product, 1, 2, 3. It doesn't change. Then we look at what is different. What's different is that we turned a bromine into an aldehyde. Now, I don't know about you, but I don't know how to turn a bromine into an aldehyde. And so instead of asking how do I turn a bromine into an aldehyde, that's my A to Z problem, way too much. I'm going to take a step back and ask, how can I make an aldehyde from anything else? Do I know another reaction or set of reactions that can do that? And the answer is yes. I know that if I have an alcohol, I can oxidize it into an aldehyde. Now I have a new problem. My new question to ask is, can I turn a bromine into an alcohol? And that I do know how to do, with one step, in fact. How do you turn a bromine into an alcohol? With an SN2 reaction. That SN2 reaction will require something like NaOH in the presence of a polar aprotic solvent like DMSO. We don't want elimination. We want to make sure it goes substitution. Once I have the alcohol, I want a partial oxidation, PCC. I will give you the reactions on the side for each one. This way, if a reaction comes up that you don't recognize, you're not as comfortable with, now you know what you have to review. So PCC, that's an oxidation reaction, or the redox chapter, and that's it. I couldn't come up with my product from start to finish, but in thinking about it one step at a time, one step back, I got the final product. Again, this was an easy problem, but I want you to think about it less in terms of easy or hard and more in terms of the system. Does the system make sense? Because if it does for something simple, then it will hopefully also make sense for the more difficult problems and save you time and frustration and stress and everything negative on your exam. So let's try, a lot of students will not have learned oxidation in Organic Chemistry 1, so that will make it a harder problem, but still doable. Let's pretend we don't know the oxidation reaction, but we still want to come up with the same exact product. Once again, I don't know how to go from a bromine to an aldehyde, so I'll cross it out and I'll just ask, how do I make an aldehyde? If you haven't learned oxidation, a different reaction that you do know is to turn an alkyne into an aldehyde. So that would be a 3-carbon alkyne. And I kind of jumped ahead, so let me just quickly review. Question 1, what's the same? All of the carbons. Question 2, what was different? Bromine turned into an aldehyde. If I take a terminal alkyne and I react it with a hydration reaction, we'll do the reagents shortly, that will turn it into my aldehyde. Well, it'll be a 2-step process, which we'll get into in a moment. But now I have a new question. How do I turn a terminal bromine into an alkyne? Once again, I don't know how to do that. There's no 1-step reaction that will turn bromine into an alkyne. And so we ask the same question again. If I can't turn bromine into an alkyne, what do I know how to react to turn into an alkyne? To make an alkyne, you would want to do a double elimination. Eliminate once for the first pi bond, eliminate twice for the second pi bond. That means we need to have 2 halogens, 2 leaving groups on the molecule. I have an option of putting both of the halogens on the same carbon, or both of the halogens on opposite carbons or nearby. And I'm going to choose to do the nearby carbons because if I think about it, I have to think about what reaction could potentially get me there. And I know that an alkyne can give me a geminal dihalide, 2 halogens on the same carbon, but an alkene can give me 2 halogens on neighboring carbons. So this right here is a vicinal dihalide. Vicinal in the same vicinity, they are next to each other. And the reason I knew to go this way is because I have to think 1 step back. I have to think of a product that I know how to make, and I know how to make it from an alkene, which then brings me this question. Can I turn my primary bromine into an alkene at that same position? Absolutely yes. So I didn't know how to do it in 1 step, so I thought a step back. I still didn't know how to do it this way, so I stepped it back, and now that I know how to do the transformations, let's go ahead and fill in the reagents. To go from a primary bromine to an alkene, I will need to do an elimination reaction. Because I only have 1 option, it doesn't matter what I use, so I will use NaOH and H2O. We'll add some heat just to make sure it goes elimination. This is an E2 reaction. Once I have my alkene, how do I get a dihalide? How do I get 2 halogens on there? I react it with the halogen Cl2 in an inert solvent like CCl4. This is an alkene addition reaction. Once I have the dihalide, I do a double elimination. That will be using a very strong base, NaNH2 in NH3 liquid. This is an alkyne reaction, or the alkyne chapter. And finally, to go from the alkyne to the aldehyde, it's technically a 2-step reaction, but you don't have to show both steps. If I react this with some version of boron for hydroboration, for example, B2H6, and then THF for the solvent, is step 1. Step 2, I will use NaOH and H2O2. This right here is also in the alkyne chapter. Again, I'm putting the reactions here so you know what to review if you don't recognize them or don't remember them. This will give me an intermediate that is not isolated. Only 1 pi bond will break, and I will get my OH at the terminal carbon. This is an enol. The enol is not stable, not isolated, but you don't have to do anything because it will automatically undergo keto-enol tautomerization. The enol will tautomerize or isomerize to give me the keto, or in this case the aldehyde form, and that gives me my final product. Nirmal, if you're referring to the book, I have seen it, yes. So looking at this, when I saw the initial problem, I couldn't come up with the steps because my brain is thinking bromine to aldehyde, how do I get there? But, and I hope you can agree with me, let me know in the comments. If you ignore the reactant for a moment and then ask the question, do I know how to get this from anything? Do I know how to get this from anything? And then work your way backwards. Does that feel like an easier, more doable, systematic approach that will help you not freeze on your final exam? That's what I'm hoping for. I'm hoping that if you know the reactions, you want to not freeze so that you can actually show what you know without getting overwhelmed. Let's try another one. For this next one, we'll have a molecule that looks like this with a bromine, and you are told to use anything else to come up with a final product that looks like this. Any organic and inorganic reagents. So we ask the question. Step 1. Question 1. What is the same? My starting molecule has 4 carbons. 1, 2, 3, 4. My product has 6 carbons. That means only 4 of the carbons are the same. So let's mark that in another color. So we know 4 of the carbons are the same. I'm not going to mark the product just yet. I'll show you why in a moment. Step 2, or question 2, what is different? What's different is that I added plus 2 carbons and I turned a bromine into a ketone. This is a tricky problem, so before we even go into it, we have to consider a different question. The 4 carbons in my reactant don't have to be these 4 carbons in the product. They don't have to be numbered that way. And the reason I point this out is even though we're going to work backwards and do one step at a time, you always want to have a general idea of where you're going. And so the question to consider is if I have to turn bromine into a ketone, I kind of know how to do that. I can turn it into an alcohol, oxidize it to a ketone. I can eliminate, double eliminate to get an alkyne, turn that into something that will undergo ketoenol tautomerization. But none of that tells me how I'm going to grow the carbon chain at position 4 to add 2 more carbons. It's very easy to think it has to look exactly as you see it, and I want to challenge you that you don't and it doesn't. If you can recognize that, if you can see what I'm about to show you, that'll make it so much easier. I don't know why I jumped to such a hard problem for the second one. I meant to go in a different direction, but we'll continue and then we'll make it easier with the next one. In this case, if I want to grow the carbon chain, if you're doing advanced organic chemistry, if you've done Orgo 2, a Grignard would be your go-to. In Orgo 1, an alkyne, I misspoke, would be your go-to. Because an alkyne is great for chain elongation, and the alkyne can then be turned into everything else. This is the takeaway. If I use an alkyne for chain elongation, specifically the acetylide anion, and then turn it into something else, this right here would be my alkyne. This right here would be 2 brand new carbons that I'm adding to the chain. And that means these 4 are actually my starting 4 carbons. And so I would number it this way, 1, 2, 3, 4. Knowing that I can use bromine to make this end of the carbon reactive so that I can add 2 more carbons on this end of the molecule and grow the chain. So let's keep this in mind and see how to do it. If I know I'm doing a chain elongation with an alkyne, that's an SN2 reaction, I need to turn this into a molecule that can have a leaving group at the end to be attacked. And so the reaction that I want to start with is moving the bromine over 1 position. I want to move the bromine over to here. What reaction do you know that will move a halogen 1 position over? This brings up one of the patterns that I want you to recognize. In organic chemistry, even though you have to come up with all the different things, there are certain patterns that will repeat themselves over and over and over. And as soon as you recognize, I need to do X, and your brain sees a pattern, you immediately know what to do. So the first pattern I want to show you is moving a functional group. If I have something like a bromine, and I want to move it over 1 carbon. Okay, so this is moving the functional group pattern. You'll worry about it once, right now, today, and as soon as we're done with this, you'll never have to figure this out again. You always go back to this pattern. And the pattern is as follows. I actually don't know how to move the bromine. It is not doable in one step, but the pattern here is going to be a series of addition and elimination. Or I should say elimination and addition. Same thing, but in reverse. If I eliminate the bromine in the direction that I want to add the new halogen, in this case, I'm going to eliminate it towards the end of the molecule. I can then do an addition reaction to put a bromine back on the molecule. How do I eliminate it towards the less substituted side? This would be an E2 reaction that gives me the Hofmann product. What is it? 1F and 2 N's, right? The Hofmann product, that means I have to use a big bulky base like tert butoxide. Dissolve it in tert butanol at heat. That will give me the less substituted pi bond. Then, to get the bromine on the primary carbon, I want to do a radical alkene addition. So this will be under your radical reactions. And I'll react it with HBr and peroxides to get the bromine adding at the anti-Markovnikov terminal carbon. If I wanted to do it in reverse, then I would just eliminate in this direction with a regular base for the Zaitsev product and do HBr without peroxides to give me a Markovnikov addition. So those are, actually, why am I saying it in hypothetical? Let me show you the other pattern. If I want to do it in the opposite direction, we'll get the pi bond that is internal and then get the bromine that is on the more substituted carbon. To accomplish the reverse, when we're going towards the more substituted, we'll use a small base like NaOH or NaOET, dissolve it in its own conjugate solvent like ETOH, add heat because why not, to ensure elimination. Then in the next step, we're going to do an alkene addition reaction. HBr, you don't have to show a solvent, but if you want to, CCl4, something inert. So this pattern is what I call moving the functional group. And all you do is addition, elimination until you get it where it needs to go. So now that we know the pattern, we see, oh, I need to move the bromine to the terminal carbon. We know it has to go through an alkene intermediate, where the alkene goes to the less substituted carbon and then an addition. Let's go ahead and fill it in. For the first step, we have tert butoxide dissolved in its own conjugate solvent and add heat to drive the reaction forward. Not that it could go reverse. It's to make an unfavorable reaction or a reaction with high activation energy happen faster. And then we'll react with HBr and peroxides to get bromine on the primary carbon. The purpose of doing all this was to create a good alkyl halide that we can attack with an alkyne for an SN2 reaction. But where will that go? So let's see what specifically that needs to look like, but by now looking at the product and working our way backwards. Nirmal says, your voice at sudden resonates from melody to a horrific thriller one where you ask questions. Well, hopefully it's less scary to do in a session, and then your exam won't be scary. Nirmal, I don't understand your benzene question. So what could I have had here if I know it came from an alkyne? I know the alkyne can turn into a ketone if I do oxymercuration that undergoes ketoenol tautomerization. What does that look like? The alkyne, those are the two new carbons that I added. The red line showing the bond that formed from my starting molecule. Actually, let's do it the other way so I don't have to flip it. So I have the alkyne, the brand new bond, and this is linear because the alkyne is sp hybridized, and then 1, 2, 3, 4 carbons. Excellent.
Now, how do I go from here to here? Very easy. All I need to add is an acetylide. The acetylide will attack like this in an SN2 reaction, kick it out. That will give me the alkyne, which I then react with HgSO4 in H2SO4. This will give me, just like in the last alkyne reaction that we saw, an intermediate that looks like this. So right now we have an enol, we have an alkene and an alcohol on the same carbon, not something that we can isolate because it'll automatically undergo keto-enol tautomerization and give me the final product. All right, so let's see what other patterns we can focus on, because if you have the patterns understood, as soon as you recognize the pattern has to happen, you will be good to go. I already showed you the pattern of moving the functional group. The next pattern that I want to show you is what I call the something from nothing. The something from nothing reaction is where you have a molecule minding its own business, and you are asked to turn it into anything. Whatever group you want to put on it. Why do I keep choosing the light blue color? You're asked to turn it into something that has something on it. But if you have nothing, let's go back to our questions. Question 1, what's the same? All the carbon atoms. Question 2, what is different? We went from nothing to having a bromine. So the question is, how do I get something on the molecule when I have nothing? And the something from nothing comes from a radical. Again, a radical reaction, very important because we want to be able to add something onto the molecule. If I take my starting molecule and I react it with bromine, Br2, in the presence of peroxides, this will give me a bromine, not where I want it, but at least it gives me something that I can react on the molecule. If I have something to react, I can move it, I can change it, but if I have nothing on the molecule, I'm stuck. So I have my bromine, but bromine is not where I want it. I want my bromine at the terminal carbon, which now that we recognize that we want a move the functional group reaction, we already know the pattern. To move a functional group, you do additions and elimination, or elimination and addition. First, I will eliminate in the direction that I want to put the final bromine. So I'll put a pi bond there, and then I'll do an addition to get the bromine where I want it. How do I do an elimination towards the less substituted carbon? We already saw tert butoxide in tert butanol with heat. And how do I get bromine primary? Very simple. We already saw to react HBr and peroxides. I don't know that I showed this to you before, so just as a quick reminder, this is in the radical chapter. This one right here is in the E2 chapter, or the E2 reactions under the SNE chapter. And this one right here is an alkene reaction, alkene chapter. Okay, so these are two patterns that are going to help you so much because they come up over and over and over. Before I continue, if you haven't already, make sure you give this video a thumbs up, subscribe to my channel so you don't miss out on any new videos. And why don't we do some more practice implementing these two patterns, but let's change it up a little to see what we can switch up, because I don't want you to be locked into just one thing. I want you to be thinking big picture. For this molecule, I'll give you a chlorine on a wedge, reacting somehow, some way to give us an alcohol at the end. All right, question 1. what is the same? We have 4 carbons in the chain. Question 2, what is different? Well, the starting molecule has a chlorine on carbon 4. On carbon 2, and the product has an alcohol on what appears to be carbon 4. What reaction do you know that will move a functional group 2 positions over? Not 1 position like we saw before, 2 positions over. We could do the move the functional group pattern, but you don't actually have to move it 2 positions over. Professors like to trick you by switching the molecules around. Here's what I want you to recognize instead. I can number this from any direction, right, left, left, right. So what if I number it this way, and now I just have to move the chlorine from carbon 2 towards alcohol, carbon 1. I'm moving the position of the reactivity 1 carbon over. But how do I do it if move the functional group had to do with halogens? How do I do it with alcohols? Actually, the same exact way. If you are going to eliminate and get an alkene, you can then add whatever you want. It does not have to be a halogen. And so I want to eliminate the chlorine towards carbon 1. We already know to do that we'll use tert-butoxide in tert-butanol and heat. That will give me a pi bond that looks like this. And then, instead of adding a halogen, I said elimination and addition, we'll do an alcohol addition. What reaction is going to give me a primary alcohol, not following Markovnikov's rule, so an anti-Markovnikov product? That will be hydroboration. To do that, I'm going to react BH3, THF, NaOH, H2O2. That's step 1, and that is step 2. Once again, this was an E2 reaction, and this right here was an alkene reaction. All right, let's jump over to the comments. If in my exam they say no additional carbon sources should be used for the carbon incorporated into the final product, can I still use the alkyne as a nucleophile? Ava, there are 2 types of synthesis that you're going to see. One is like this, where you cannot add any more carbon, but you don't have to because the number is the same. The other type is what I did with you earlier, and that is where you do add carbons in. So you will have to be allowed to add carbon if the chain is going to grow, or they will give you 1 molecule and make you react the molecule twice. Meaning, sometimes you'll be given, let me see, a very common type of problem is starting with only acetylene plus any other inorganic reagents, meaning non-carbon incorporated into the ring or into the molecule, come up with, and then you're told to form all kinds of products. So let's use this example, and we're going to synthesize something that looks like this. Again, starting with acetylene and any inorganic reagents, we have to come up with a product. Now acetylene is a 2-carbon chain. So we have to map this out from starting to ending and say that if we're starting with acetylene and we want to come up with a product that looks like this. Question 1, what is the same? 2 of the 3 carbons have to be what I started with. So if we call this 1 and 2, this is 1 and 2. Question 2, what is different? I have a couple of differences. I added 1 carbon. I also turned a triple bond into a carbonyl. What reaction do you know that adds only 1 carbon? We can't actually ask that question. We're only allowed to use 2 carbons. How do I add 1 carbon to the chain? How do I grow my chain by 1 carbon if the only thing I'm allowed to do is add 2 carbons? What I will want to consider here is adding the 2 carbons and then cutting one of them off. That would be the only way to approach this. And so we'll consider, what could this have come from? If I go one step back, and I know I have to turn 2 into 4, what 4 carbon chain will allow me to cut a carbon off to give me 3? Oxidative cleavage. And because I have an aldehyde and not a carboxylic acid, I would want to go with ozonolysis. Oh, interesting. Ozonolysis would give us... I'm trying to think what students would have learned in the alkyne chapter, because there's another way that we can do this in case you didn't learn the reaction that I'm thinking. Yeah, ozonolysis will give us a carboxylic acid. So this is actually a trick question, because the 4 carbon chain that I would have had to cleave would have been this. This would be carbon 3 is the new one I added, 3 and 4, 1 and 2. So now we have, well, we just turned this problem a lot more tricky than I intended, but hey, that's good practice. So let's go this way and just give ourselves a lot of room to work this out. How do I go from acetylene to 1-butene? Let's first think about how we're going to grow the chain. Acetylene, if I turn this into an acetylide anion, can then undergo an SN2 reaction, where if I react it with a 2 carbon chain with a leaving group, for example a bromine, I will get something that looks like this. My 2 green carbons, and let's make this one purple so I can follow everything along. My 2 green carbons, a new bond, and then the 2 purple carbons. That actually didn't need as many steps, because the very next step I can just reduce it. Let me draw it in the other direction so that you can follow the carbons. This is what I'm adding. That would not be the purple one. So this would be my 2 carbons. Attached to that I have the new bond going to the alkyne, like this. And that means the 4 carbon chain that I have over there, that is carbon 1 and 2. I'm going to have to change the numbering because we'll follow the colors and I'll number everything at the end. So I have the 2 purple carbons. The red is the bond that connected them. And then the green would be the one that came from this one. So this is all said and done. It looks pretty good, except we were only allowed to start with acetylene. So another synthesis I have to do is show how I got this from acetylene so that I don't lose any points. And that would be, I'll just put the arrow showing how I got this. This right here would have come from an alkene, which would have come from an alkyne. That was actually not so difficult. All I have to do is get a halogen on there. All right, now that we have the steps, let's go ahead and fill in the reagents. To turn my alkyne into an acetylide anion, I'm going to react it with NaNH2 in an H3 liquid. That's a very strong base. It'll deprotonate. This right here, if I mix the 2 together, is already good to go. I don't need to add anything. To turn this, to get this alkene, I have 2 options. Because it's terminal, it doesn't matter cis or trans, because there is no cis or trans for a terminal alkene. And so I will choose to do H2 with a Lindlar's catalyst for a partial reduction. And last but not least, I will do ozonolysis, where in step 1 I will use ozone, and step 2 I'll use DMS. Let's go down to the other one. Once again, we can do H2 and a Lindlar's catalyst. That will give me an alkene, and then we can do HBr and peroxides to give us our primary bromine, an anti-Markovnikov addition, or in this case they're both primary, so there's no Markovnikov going on here. And that's it. That's my reaction come together. So Ava, I believe that was your question initially. Does that make sense? Is that clear? And for anyone else who was following along and has questions, go ahead and type it in. Tiffany Lamb, you are very welcome. Okay. Let's see what we can practice next. So that one was a nice and tricky problem. Hopefully that gave you quite a few tips in terms of how to think about it. For the next problem, let's look at something like this. Say I have a molecule that has a benzene ring with 3 carbons attached, and somehow, someway, you are told to come up with a product that has benzene, still with 3 carbons attached, but an alkene on there. When you first look at it, whoops, did not mean to do that. When you first look at it, it looks like a pretty straightforward problem. All I have to do is stick a pi bond on there. Can't be too difficult. But the question is, how do we get there? Given that it's not just a pi bond, it's what is the same? All the carbons. What is different? The fact that we have nothing on the molecule going specifically to a cis pi bond. As soon as you recognize you have nothing going to a cis pi bond, you say, oh, the something from nothing reaction. Let me put a halogen, because if I have a halogen on the molecule, I can start moving it around to wherever I need. So I have my 3 carbons and I put a halogen. Oh, I said I was going to go back and number it. I almost forgot, so let's do that. If we call the green carbons 1 and 2, 1 is the position of attachment, and that would be here. The incoming purple that gets attacked, that's 3, and this is 4. So for each one, that'll carry through as 3 and 4, 3 and 4. So that would be your numbering for the last one. If I do this something from nothing reaction, I get a bromine. If I then eliminate, I will get, where did it go? I will get something that is, well, relatively stable. I can't control the pi bond if all I do is an elimination. That is not what I'm looking for. I'm looking for a cis, not a transalkene, and I need to guarantee the cis alkene. The only way I know to guarantee a cis alkene is to do a partial reduction starting with an alkyne. So that is why this is a tricky question, because I have to add that step in, and that means I will have an alkyne, except it's not in that position, it's right there, like that. So the question is, how do I get an alkyne from an alkene? This is another pattern that we should recognize. So we had the something from nothing pattern here. We should have probably put the patterns together, but I'll put the pattern down here for you. The pattern that I want you to recognize is anytime you need to go from an alkene to an alkyne, it's not as simple as just adding another pi bond. You actually have to break the pi bond to reform it. That means if I have an alkene, I first break the pi bond by doing a double halogenation so that I can do a double elimination, and bam, very easy if you recognize it, very hard if you don't know to look for the pattern. And the way this happens is very simple. Cl2 in the presence of an inert solvent like CCl4, and then a double elimination with a very strong base, NaNH2 in NH3 liquid, not in water. Water will not help this reaction, and that's my pattern. Break the pi bond so that you can reform 2 pi bonds. Let's apply this pattern here. To break the pi bond, we're going to have a double halogen. So let's put 1, 2, 3, 4. Actually, just 3. So let's put 2 bromines and then react by removing both of the bromines, eliminate both bromines to get a pi bond. Let's go forward and fill in the reagents. There's something from nothing, a radical reaction, Br2 in peroxides. This is going to give me a bromine at the most substituted, most stable radical intermediate position. This is the radical chapter. I'll just squeeze that in here. Next, we want the pi bond. That'll be elimination with any base. NaOET is a good choice because I felt like it, but any base will do in this case. And heat to drive the elimination. Then you want to break it with a dihalide, so Br2 in something like CCl4, double elimination, NaNH2 in NH3 liquid, and we have our product. Oh, no, we don't have a product. We still need the cis pi bond, so that will be H2 in a Lindlar's catalyst. That will force it to do a partial reduction with a cis alkene, and that is my final product. Oh, NBS. I hadn't even thought of that. Yeah, so in Orgo 2, you'll learn NBS. I don't think students learn it in Orgo 1, but NBS is another way to add bromine to an allylic or benzylic position. So instead of breaking a pi bond, NBS will actually put the halogen next to the pi bond or the benzene ring. For students who joined late, yes, to get a link to the recording along with the workshop notes and the worksheet of practice problems, these problems, but a couple more to continue applying the skills that you learned, go to the pinned comment, sign up at leahforsci.com/orgolive. I will send it to you later because my kiddo is going to be home soon. I'm going to take a break for a couple hours, spend time with him, and once he's down, I will write up the worksheet with extra problems for you and email it out. Go to leahforsci.com/orgolive to sign up, but also make sure if you haven't yet, subscribe to my channel, give this video a thumbs up if you're enjoying it so far. If you're not enjoying it, well, I assume you would have left. So if you are here, I want to see a thumbs up and I want to see lots of hearts in the comments. And let's go to another one. This next one is a fun problem because it looks scary, but if you recognize what's going on, it's actually a very easy problem. Whoops, I don't know why I'm redrawing the starting molecule. Let's try that instead. Okay, maybe not very easy, but we'll call it straightforward enough if you know what to do. Somehow, some way, we want to come up with this. When you first look at it, you're starting with a ring, you're ending with a chain. You have nothing on the ring, you have 2 aldehydes on the chain. There is so much going on here that it looks really, really scary. Unless we take a step back and we ask question 1. What is the same? How many carbons do I have? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, not so scary. All I have to do is think of opening the ring, because question 2, what is different? I have a ring that turns into a not ring. I have nothing on the ring. I have aldehydes in my product. There's a lot that I have to do, but instead of worrying about all that, let's just think, take a step back. What reaction do I know that will open a ring? If I can figure that out, that's the middle, then I can get there and I can go from there. What reaction will open a ring? I need to do some kind of oxidative cleavage. And because I know I'm getting aldehydes, it would have to be ozonolysis. So if I take this one step back, via ozonolysis, I know I'm going to get the 2 aldehydes. All I need to do is give my ring a pi bond, because the pi bond is exactly how ozonolysis is going to break it open. And then I have a new reaction. How do I go from a ring with nothing to a ring with a pi bond? Well, that's pretty easy. If I have a ring with nothing, before I can even consider the pi bond, I have to consider the something from nothing reaction because I need something to react. Something from nothing is going to give me a bromine or a chlorine. I chose the bromine. And if I have a bromine, I know very easily how to eliminate. So do you see how it looked so overwhelming? But as soon as I recognized my pattern, something from nothing gave me a bromine. Bromine lets me eliminate to an alkene. And if I want a ring, I need to break open a ring. I'm sorry, if I want a chain, I need to break open a ring. That will come from an alkene and ozonolysis. So let's figure out then what we do here by filling in the reagents. Step 1, something from nothing. We've seen this so many times by this point that you should be very adept at saying Br2 and peroxides. That will give me the bromine. Once I have the bromine, it's very easy to eliminate with any strong base like NaOCH3 in CH3OH and heat. And then ozonolysis we've already seen before. Step 1, use ozone. Step 2, DMS, and boom, that's my product. The chapters to review for Br2 and peroxides, that is your radical chapter. This one right here is an E2 reaction, and this one right here is an alkene reaction. All right, I'm thinking which one to show you next. Let's try another moving the functional group just because I want to mess with the patterns in your head. Not that I want to mess with your head, I want to teach you to pay attention to allowing different things to happen and not be rigid with the one reaction. Somehow, some way, I want you to take that starting molecule and turn it into a product that looks like this. All right, so let's take our 2 questions. Before I continue, I see, do you have any suggestions for the full year ACS exam? Jacob, not only do I have a suggestion, I actually created a final exam pack specifically keeping in mind students who take the ACS. The ACS is not just a multiple choice exam that tests you on everything. It's an exam that forces you to think about all the details because with multiple choice, they can test you on anything. You have to think quickly. You have to think under pressure. You don't have a lot of time. You have to get a ton of questions right. And so what I did was I wrote a practice final exam. I then went and broke it down step by step, every single question telling you how to approach the choices, how to think under pressure, how to come up with it quickly. And it is available on my website. If you go to layerforsci.com/final exam pack, I have an Orgo 1 exam and an Orgo 2 exam. And so if you're doing cumulative, you definitely want the Orgo 2, but if you're doing cumulative, you probably want both so you can practice a little bit of everything. All right, so going back to this one, let's see. Question number 1, what is the same? And question number 2, what is different? So take a look at this for a moment while I look at the other comment, persistently ignoring me. Yes, I'm choosing the relevant comments to address. And so if the comments are not relevant, I will answer them later if you leave them in the chat. I'm not ignoring you, I just can't go through all the comments right away. All right, so looking at this right here, what is the same is the carbon chain. I have a 4-carbon chain with a methyl group coming out of it. What is different is that I have a bromine on, if I number it 1, 2, 3, 4, bromine on carbon 4 turns into an alcohol on carbon 3. In a situation like this, I can go forward, I can go backwards, and I can meet in the middle. But I do know that I have to slowly move my functional group in that direction, and so I'm going to start out with the move the functional group pattern and see what happens, because you will be surprised at the next step. The first thing I want to do is eliminate. We've already seen this one. And once we eliminate, we want to add, well, we would normally want to add a bromine here so that we can eliminate there, but here's what I want you to pay attention to. If I do a Markovnikov addition reaction where there will be a carbocation intermediate. The intermediate for this step is going to be a carbocation here. And this is another pattern you want to recognize. Anytime I have a secondary carbocation near a tertiary carbon, I will have a carbocation rearrangement. I will have a hydride shift. And so that is going to be the carbocation position right there. That means I don't need another step. My one next step will actually give me the final product as follows. If I react this with H2SO4 in H2O, pi bond breaks, carbocation is here. Carbocation will move through a hydride shift and then alcohol adds, immediately giving me my final product without needing one more intermediate. Let's fill in the reagents here. This has to be tert-butoxide because we're going in, actually it doesn't have to be tert-butoxide because we're going towards internal. Let's do NaOCH3, CH3OH, and heat. I don't know why that looks so funny. CH3OH and heat. And then H2SO4, H2O will give you your final product. Okay, so with that, to get a copy of the notes from today's session, the worksheet with additional practice problems, a link to the recording, go to leahforsci.com/orgolive to sign up. Also, if you'd like more sessions like this, along with in-depth practice, tons and tons of problems with video breakdown, and the ability to ask me questions every day in my private members-only tutoring group, come join me in the Organic Chemistry Study Hall. So the link is leahforsci.com/join. You can post your daily questions, and I will not just give you answers, I want you to learn from all your questions. So if you tell me I'm not sure what to do here, I'll give you a video, I'll explain the piece that you're not understanding, I'll walk you through it. And if you have your final in a couple of days, being able to ask me questions every day will eliminate the need for a tutor, give you access to all the topics that you're struggling with, because I have in-depth, step-by-step, lengthy, intermediate to advanced, beginner, intermediate, and advanced videos in the study hall as well. And you can find all of that at leahforsci.com/join.